Hey everyone, today we're just going to go through another example of related rates. We've already done two videos on the idea. Today we're going to apply that information, that knowledge, to geometric solids, geometric shapes like spheres and rectangular prisms and cones and cylinders and things like that. So you're going to see an example of that. And I'm going to tell you right now that this problem is pretty heavy. It's pretty difficult to grasp. Not necessarily because of the calculus, but because of the geometry that's related to it. Notice how I use related because we're talking about related rates. Anyways, let's go ahead and take a look at this one example for today. Water runs into a conical tank at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Now we read that and we go, okay, I understood all the words, but that's a lot of information there, right? So we're going to have to break it apart into pieces. Remember, the first thing we want to do when we're talking about related rates is to draw a picture of what we're talking about. Well, it says that this is a conical tank. A conical tank, what's that mean? It means it's a cone. And it says that it's point down. So the vertex of this cone is downward. Why would we ever want that? Well, think of a funnel, right? We would pour liquid, oil, water, something into this funnel, and then maybe it would leak out or funnel out into something that we need it into. But there's our tank. Now, what does it say about this information? It says that water is running into the conical tank. So maybe we have a hose or something that's pouring into this tank. Now, as time goes on, the water level is going to rise. And so maybe this is the water level, we'll just arbitrarily say. So that's the height of the water. And it says that water is running into the conical tank at a rate of 9 feet cubed per minute. Well, what does that mean? What is 9 feet cubed? Feet cubed is talking about volume. And it is, I'm going to go ahead and write this down, the rate. So dV dt is 9 feet cubed per minute. Well, what volume is changing? The tank isn't changing. It's the water that's changing. So when we're talking about the volume, we're not talking about the volume of the tank. We're talking about the volume of the water. So keep that in mind. Now it says that water is being poured into the tank. So that means the volume is increasing. That's why the rate is a positive value. The volume is increasing, so dV dt is positive. Now, it says the tank stands point down and has a height of 10 feet and a base radius of 5. So let me go ahead and write that in here. It says that the height of the tank is 10 feet. Now, some of you might be saying, well, why aren't you writing that off to the side? Because this information is dealing with the water, not the tank itself. So I'm just writing this information off to the on the picture because this is dealing with the tank, and the tank isn't changing. Now, the next point says, it says, how fast is the water level rising when the water is 6 feet deep? Well, what does it mean for the water to be 6 feet deep? Well, that would be this length here. I'm going to use blue. This length is what we're talking about here. Now, I don't want to put 6 here. We don't want to put 6 there because the water level is rising. So this number is changing. So I'm going to put this as a variable. It's something that's changing. But over on the side, over in my notes, I'm going to say I'm asking for the moment in time when the height is 6 feet deep. Okay, or when the water is 6 feet deep. So these things are things that are changing or part of the video, if you would, playing out. And so I don't want to put those numbers in here because these numbers, if I put numbers here, imply constant values. So I don't want to do that. And then the question says, how fast is the water level rising? So the question is, how fast is this value changing? So we're saying, what is dH dt? That is the question there. What is dH dt? So now I have everything that it gave me. I know what it's asking for. I've got a picture. The next step is to create an equation that relates these things. Now, this is where a lot of students go wrong on this particular type of problem. They think that we're asking about the tank itself because I gave you information about the tank. Now, that information is going to become useful later on, but that's not what the question is about. The question is about the water, which is a totally separate thing than the tank. The water is inside the tank, but the information about the water is different than the information of the tank. Okay? So, how can I relate the equations or the information that I have about the water, not the tank? Well, here we're talking about volume and the height. So what's an equation that deals with the volume of a cone? Remember, the volume of a cone is 1/3 the area of the base. In this case, the base shape is a circle, so 1/3 pi r squared, and then times the height, right? The volume of anything is always the area of the base times the height, pi r squared h. But when we're talking about cones, where it goes to a point, we take that and divide it by 3. So that's the volume of the cone. Now, remember, we don't plug anything in until after I take the derivative. I want to take the derivative of volume in respect to time. I want to take the derivative of height in respect to time. So that would automatically imply that t is our variable, which means everything else here is a function of that, including the radius. Now notice pi is a constant, so anyways, we're going to take the derivative of this. So the derivative of v is dv dt equals. Now let's go ahead and break this apart. We're going to apply the product rule, and I'm going to say that the first thing is my first piece of the product, and then h is my second piece. So the derivative of this first thing is going to be 2/3 pi r, right, power rule. But then I have to use a chain rule, so what's the derivative of r? Well, that would be dr dt, and then times the second thing, so times h, plus the derivative of h, which is dh dt, times the first thing, which is 1/3 pi r squared. So there is my derivative function, or my derivative relationships, I should say. I'm going to go ahead and clean it up by moving all the constant values to the front of each term and moving the dr dt and the dh dt to the end, just so it looks a little bit nicer. So 2/3 pi r h times dr dt plus 1/3 pi r squared times dh dt. Now, from here, we would normally just plug numbers in and we would have our information. We would have enough information to solve. Notice, so I've got dv dt, that's one thing. I've got r, I've got h, I've got dr dt, r is already over there, I got dh dt. So I got 5 things here that I don't know yet. 5 things. Over here, I gave you 2 things. So that means there's 3 things I don't know. Well, one of them is the question, so that's good. That means there's 2 things I don't know, right? Now, we have to be careful here. The radius and the height, again, are not the radius of the height of the tank. It's the radius and height of the water. So I'm going to go ahead and put r here so that you guys can see that. Let's go ahead and plug in what we know. We know that dv dt is 9. So 9 equals 2/3 pi r. I don't know what r is, so I'm just going to leave that blank for right now. H is 6, so I'll plug that in. Dr dt, I don't know what that is either, and I'm going to need to know what that is because that's not what the question is, right? So I'm going to go ahead and leave that blank. Plus 1/3 pi r squared. Again, I don't know what r is, so I'll put something squared. And then dh dt is the question that I have, is the question that I'm asking. So I need to know what r is, I need to know what dr dt is, and then what r is over here. So now we got to come up with something else to figure out what r and dr dt, what those values are. Well, we go back to our picture, and we see that the radius and the height, how are those related? Somebody might say, well, they're the Pythagorean theorem. You know, you got a right triangle here. That's r and that's h. We're supposed to set up the Pythagorean theorem. Yeah, but then we're throwing in another variable. And that variable isn't represented in any part of this problem, so that could be a problem. And the other thing is, because we're talking about volume and everything else, that's the diagonal length. That has nothing to do with it. So I wouldn't do the Pythagorean theorem. I don't think that's going to be beneficial. Well, then we ask ourselves, what information haven't I used yet? Well, I haven't used the idea that the radius of the tank is 5 and the height of the tank is 10. And the two cones, if you would, the smaller cone and the bigger cone are related to each other. The smaller cone sits inside the bigger cone. If I poured enough water, the cones would be the same thing. We would say that the cones would be congruent to each other. But because they're not the same height, one is smaller than the other one. They're not congruent, but they're very, what's the word? Very similar, right? They're similar to each other. And so here's the relationship that might be a good relationship to see that's going to help us out in this problem. Okay, we have the big cone, and this line represents the height. This length represents the height of the whole cone. Okay. Then we also know that the radius of the whole cone is 5, and then we cut here something like this to represent the water's height. So this length is height. This distance is h. And then this distance here is r of the water. And so you guys should be able to recognize this back from geometry, that we have similar triangles here. Why do we have similar triangles? Well, this small triangle and the big triangle share this bottom angle, so that's one angle that's the same. And these two lines are going to be parallel to each other, which implies that these two angles are the same because they're corresponding angles. And now I can say that those two triangles are similar by AA, angle-angle similarity postulate. But all that's to say, you can set up proportions between those two triangles. So I can say that h over 10, the height of the water versus the height of the whole cone, is going to be equal to the radius of the water over the radius of the whole cone. So I have this relationship here that actually helps me out quite a bit. Let's see what happens. I can simplify this by cross-multiplying. I get 5h equals 10r. And then divide by 5, I get h equals 2r. That's nice. Nice, clean relationship there. How does that help? Well, I need to know what r was. That's what I was trying to figure out here. And what dr dt is. Now, this doesn't really help too much. It helps me because if h is 6, I can figure out r. That's nice. So I can go ahead and plug in 6 here, and I end up with r equals 3. So that's good. I can plug that in. That's 3, and that's 3. But I'm still missing this dr dt. I need another rate. I need another derivative. Well, let's take a step back. I keep grabbing my eraser that smudges, so I'm just going to use this. Let's take a step back here. I need another derivative relationships like I did here. Let's see what happens. If I take the derivative in respect to time, because I need dr dt in respect to time, these are both functions, so it'll say dh dt equals 2 times dr dt. Well, would you look at that? That's a good relationship. And I don't know what dh dt is. That's what I'm looking for. I don't know what dr dt is. But at least there's a relationship here, right? Now, I need to be able to plug something into dr dt, so I'm going to go ahead and solve for dr dt. So I'm going to divide by 2, so I end up with 1/2 dh dt equals dr dt. And so now I can take that and plug it in up here, okay? Now, before I do that, I'm just going to go ahead and erase this line. And that way, I want you guys to see what I'm doing. I'm trying to get rid of the variables and put them in respect to other things, okay? Before I go to substitute actual numeric values. So this is going to be dv dt, and it may not be that you don't necessarily have to do it this way. I'm just trying to show you a different approach here. 2/3 pi. Again, I don't know what r is, so I need to replace r with something that I can work with, and so I can use this equation here. If I solve for r, this is something else I can do. If I solve for r, then I would get 1/2 h equals r. And so instead of R, I'm going to put 1/2 H for R, and then H. And then dr dt, notice I solve for dr dt, that's equal to 1/2 dh dt, and then plus 1/3 pi times r squared. R is 1/2 h, so 1/2 h squared times dh dt. And so now you can see that I've got dv dt, I've got h, and I've got dh dt. Those are only three variables, and I know two of them here, and I'm looking for the third one. Okay, so now it's probably going to be easier to solve. So I can plug in dv dt, 9 equals 2/3 pi. Well, actually, before I plug in, let's simplify that a little bit more, because now I got a bunch of numbers here. dv dt equals, I've got a half, and 2/3, so that's going to be 1/4, 2/12, which is 1/6, I believe. 12, yep. And then that's going to be pi, and then h squared dh dt plus, let's see, 1/2 h squared, that's 1/4 h squared. 1/4 times 1/3 is 1/12. And then pi h squared, look at this, dh dt. And now I've got pi h squared dh dt. So these are like terms now. Those are like terms. And I erase this. So I end up with dv dt equals, getting a common denominator, that'd be 2/12. So this would be 3/12 pi h squared times dh dt. That's a lot easier to look at. And then I can plug in those numbers. So I end up with 9 equals 3/12 pi times h squared, which is 6. So 6 squared, and then times dh dt. Solving that, that's going to be 36 divided by 12 is 3. It's 1. So, wow, that's just going to be 9 equals, let's see, 36. That can't be right. That would be 9 equals 9 pi, yeah, dh dt. 9 equals 9 pi dh dt. We can divide by 9 pi, and we end up with dh dt equals 1/pi. Woo, 1/pi. Now, that rings a bell. I know that that is the correct answer, so that's good. Now, the question is, did you have to do all that simplification? And no, you didn't have to. You didn't have to plug all those values in. You could have taken this line right here, plugged in dv dt, plugged in dv dt, plugged in h, but then you'd have to figure out what r is. And so r, in this equation, if h is 6, r is 3, so you could have plugged in 3 there. And then you could have figured out dr dt. You would have had to do this part right here and replace dr dt with 1/2 dh dt. Ultimately, they end up in the same place. Whatever way you feel more comfortable with is fine. But this is my answer. And if I get that in a decimal form, so it's a little bit more applicable to what we're doing, 1/pi is going to be 0.318. So dh dt is equal to 0.318. Now the units on this are important as well. Notice over here we had dv dt is 9 feet cubed. This is dh dt. dh dt, h is a height. H is in feet. T is in minutes. So the units on this would be feet per minute. Well, let's interpret it, because that's the last thing. Now we have an answer. Let's interpret our results. We would say that the water level is rising at a rate of 0.318 feet per minute when h equals 6 feet, or when the water level is at a height of 6 feet. Now, I'm not going to write down that interpretation, but that would be what you're expected to do. Just keep in mind, you wouldn't get this in this context, but if you ended up with a negative value, you'd have one of two things going on. In this context, because we're pouring water into the tank and nothing's going out, you did something wrong. But if you ended up with a negative value, then you would interpret that. You would say the water level is actually decreasing at a rate of 0.318 feet per minute. Okay, and we do get that sometimes. If we cut a hole in the bottom of this and water leaks out, as water is poured in and water is leaking out, we have something called a rate in, rate out type of relationship. And we actually get into those types of things next semester. It's kind of cool stuff. So anyways, with that said, that's the end of this problem. I hope that this helps you, this chaos here, helps you understand related rates and gives you a good reminder of a lot of geometric principles. Look at this. We talked about the volume of a cone. We talked about similarity here. We talked about related rates. We talked about implicit differentiation. We talked about a whole bunch of stuff. Parallel lines, similar triangles, good stuff. Anyways, with that said, if you have any questions, please comment below, and I will see you next time.